Let's talk about convergence of a sequence. Suppose that you have a sequence AN. We see that this converges to L if, when we take the limit as n goes to infinity of AN, we actually get L. So really, convergence of a sequence is all about calculating limits. So let's just do a quick example. Let's say that we have, example 10. Does the sequence AN equal to 1 over n converge? So what we really need to do is we really need to calculate the limit as n goes to infinity of 1 over n. Now in this case, the numerator is a fixed constant, but the bottom is getting bigger and bigger and bigger. So this bottom part is, getting huge, and the top part is just fixed. So when we have that happen, that's exactly the situation where you get 0. So our answer here is going to be yes, it converges to 0. Okay. Just like we had limit laws when we were learning about limits in 5a, we have limit laws for sequences as well. So let's take a look at some of these sequences. One of the precursors for each of these limit laws is that we both need AN and BN. We need both of those to be convergent sequences. Okay, so we need convergent sequences. And we're going to look at examples where C is defined to be a constant. All right, so these limit laws pretty much work as you would expect. If you have the limit of the sum, you can basically split that into the sum of two limits and then add those guys together. Okay, if you have a difference, if you have the limit of a difference of two sequences, you can really just split that difference up and find the limit of AN first, and then subtract what you get when you calculate the limit of BN. If you have a constant times your sequence, you can factor that constant out. So you get C times the limit as n goes to infinity of AN, like this. Let's say you have the product of two limits. When you have the product of two sequences, so when you have two general terms that are multiplied together, the product is just going to be the product of the limits. So we can just calculate the limit of AN, calculate the limit of BN, and then we can multiply those two results together. If we look at the quotient situation, this is the one that is a little bit more interesting. We're going to take the limit of a quotient. That's going to be equal to the limit of the numerator as n goes to infinity divided by the limit of the denominator as n goes to infinity. But we have the added restriction that this limit as n goes to infinity of the denominator cannot be equal to 0 because you don't want to allow a 0 in the denominator. Finally, we have basically AN raised to a power. What we can do is we can move the limit inside the power. So this becomes the limit as n goes to infinity of AN. You can calculate that first and then raise whatever number that is to the pth power. Okay, so let's take a look at the squeeze theorem next. So the squeeze theorem for sequences works the same way as the squeeze theorem for limits in first semester calculus. So the idea, and I'll draw a picture first to help you understand, is you have your sequence AN, and it's bounded from below by some lower sequence, let's call it LN, and it's bounded from above by some other sequence, let's call it UN. So un like this. So let's say that the lower limit happens to go to some number L. And let's say that the upper limit also happens to go to some number L. Well, since an is always in between ln and un, an really has no choice. It's actually forced to go to the same number L that the other two sequences went to. Okay, so what I want to do is I basically want to take this picture and describe it more, I guess, precisely. So let's write it like this. We'll say if ln is between is the lower bound of an and un is the upper bound of an. Okay, so if this is true, and we happen to know that the limit as n goes to infinity of the ln is equal to L, which is also the limit as n goes to infinity of un. So those are two conditions of the theorem. Then we have the following conclusion. Our conclusion is then the limit as n goes to infinity of an must also be equal to L. All right, so this is the squeeze theorem. And we'll look at an example of this in class. The final thing I want to mention to you is a theorem that somewhat relates to continuity. So let's finish off this video with this theorem right here. Our theorem is going to be the following. If the limit as n goes to infinity of an is equal to some number L, and the function f is continuous, then when you take the limit of f of an, that's going to be equal to f of the limit as n goes to infinity of an, which is equal to f of L. Okay, so this is really a generalization almost of our earlier limit law right here. It's almost like our f function was x to the p, and then this said that we could move the limit inside the power. In this case, we're just moving our limit. We're moving our limit inside the function. And we could do this as long as f is continuous. All right? All right, everyone. We'll look at a ton of examples in class. Take care.